Yeah, I think we'll just wait for a couple of minutes. But if there are any questions from last time, we can discuss them now or later.
Hi, Suvrat. I had a question.
Yeah, sure. Yeah.
So I want to ask how much of this interior A tilde operator construction is motivated from this TFD or eternal eternal geometry, because it seems like you're in order to. It seems like you're naively. It seems like you're defining A tildes such that A tildes are the creation operators in the left boundary or something, right?
Yeah, but remember, it's not really the left geometry. As I said, when we did this derivation of Hawking radiation or just modes across a horizon, we needed, we pointed out that even there, whenever you have a horizon, you need some modes behind the horizon that are correctly entangled with modes in front of the horizon. So this is something that we used many times. So it doesn't. The fact that you have modes which are behind the horizon, which are entangled with modes in front of the horizon, is just something that you require in order to have a smooth horizon. So in the eternal black hole geometry, as I said, first of all, it's incorrect to say that these modes behind are like the left modes. So as we pointed out, that's not correct. We'll have a little bit more to say about it either today or in next lecture. So they are more subtle. You can't just take that to be the left modes, because otherwise you'd run into these paradoxes with the eternal black hole.
But if I repeat this construction for the eternal geometry, A tildes will match with the left modes, right?
No, they will not, because the left modes do not behave correctly in the time shifted eternal thermofield double states. So it's a common misconception. It's a very, very common error. I think that's also sometimes made in the literature, which is that we will say that the A tildes are the left modes. But if they had been the left modes, I think we discussed this maybe 2 lectures ago. If you were to do a time shift, like if you consider not the eternal black hole, but the time shifted eternal black hole, e to the IHT times the eternal black hole, then the left modes will cease to be correctly entangled with the right modes. So the left modes cannot be the correct modes to use in the time, even if you move slightly away from the thermofield double state. So this is like, so the left modes are not the correct modes to describe, even within the little Hilbert space, they're not the correct modes to describe what's happening. The correct modes are related to the left modes, but you have to like dress the left modes a little bit in order to make them correct. It's not like they're totally wrong, but you need to dress them, and that dressing is important. And if you forget about the dressing, you'll run into all these paradoxes. And in fact, that dressing has to be state dependent, as maybe, we'll say towards the end or next lecture. So the fact that you need modes behind the horizon is something that you just need for a smooth horizon, which we discussed. And it's not that that's something that's special to the eternal black hole. In the eternal black hole, it's true these modes behind the horizon are like some dressed versions of the left modes, but you just need that. That's like the condition for a smooth horizon.
Okay. Another thing I want to ask is like, these interior modes we are constructing are dependent on the state psi, and also hence on the little Hilbert space of the psi, right? Right. Then I was wondering if an infalling observer had to meet another observer who has already who already fell before him into the horizon. That kind of calculation won't be possible, because your your little Hilbert space has like very few operators acting, like small strings of operators acting on it, and you can't really detect any large coherent state kind of thing, as in any larger.
Coherent states is not the problem. The kind of process you're describing, where you have 2 observers falling in, I think that fits fine within the little Hilbert space. The things you can't describe are where you put in, an n-squared perturbation, where you change from the black hole microstate to another one. Maybe this question, if you ask again at the end of this lecture, we'll have, because that's what we're going to discuss today. So maybe I'll postpone the answer to this question to the end of the lecture. But it's not, the problem is not with just 2 observers or 2 probes falling in. Any probe you have, the geometry is not the problem. The problem is, this issue of state dependence arises if you make like a huge perturbation to the geometry. So maybe could I request you to ask this question again, maybe at the end of the lecture, and we
Sorry, do you mind if I ask a question from last session?
Yeah.
So I'm a little confused about this point. If I'm not mistaken, if you want to create these mirror operators in the language of Tomita-Takazaki theory, you have to use this modular conjugation operator, right?
Yes.
So in that case, you need an algebra, but you explicitly mentioned in the last session that these simple operators do not form an algebra. Are you working with like bounded operators on the little Hilbert space?
No, you don't. It's commonly defined with respect to an algebra, but in fact, you don't need what you need is, so these operators are defined this way. So notice all you need here actually is a set of operators. So that's why I said that this set of operators A was closed under Hermitian conjugation and was also closed under linear combinations. But provided this is a set which is a linear Hilbert space, the definition of this kind of an operator, which is the operator I wrote down, actually goes through. There's this paper it's true that Tomita-Takazaki theory is commonly done when the A is an algebra. But just to define this operator that we have here, this S operator, and then if you wanted to define S dagger S, and all of these would be defined on the little Hilbert space, you don't need A to be an algebra, because to define this operator, you see, you never take products of A. So sometimes you might it's true that sometimes you might need at least the inner product of elements of A with other elements, but you never need to take arbitrary products. So I don't have the reference at hand, but there's a paper we wrote on precisely this issue, which is called Quantum Information Measures for Restricted Sets of Observables, in which we discuss this. So you're right that Tomita-Takazaki theory is usually described for algebras, but to define these operators, you don't actually need an algebra. You can define it even if these A's are not algebras.
I see. Thank you.
Okay. Okay. So if there are no more questions, we can start the lecture. Today we are going to discuss, I think, extremely interesting physical effect, which is called state dependence, which already was discussed a little bit in the questions that we had right now. But before we go on to state dependence, I just want to tie up some loose ends from yesterday. The two loose ends I want to tie up are the question of how these mirror operators interact with conserved charges, and how they interact with states that are not equilibrium states. And both of these questions were important at some point in the literature. So I just want to go through them briefly, and then we will turn to the issue of state dependence. Let me just remind you, yesterday we defined these operators, which we call A omega tilde. We define more general mirror operators, but throughout this lecture, I'll just use this as a representative of the set of mirror operators. Of course, you have A omega dagger, you have polynomials of A tilde omega, and so on. But what I'm saying right now is pretty generic, so I'll just write A omega tilde as a representative of a mirror operator. And what we proved yesterday was that if you had a simple operator an, then we had the property that this was 0. So it was not the case that A omega tilde with an was equal to 0 as an operator. So in fact, this is not equal to 0. Nevertheless, this operator is such that it annihilates the state psi. So these mirror operators were designed so that the commutator was undetectable within simple experiments, although the commutator was not 0, and in fact could not be 0, because as we discussed yesterday, the modes of the field generate the entire algebra. So there is no operator that commutes with all modes of the field. Okay. But as we emphasized, also earlier when we discussed these modes behind the horizon, and when we discussed how you have to address these operators behind the horizon, we also explained that these mirror operators should not commute with everything outside the horizon. And in particular, they should not commute with the Hamiltonian. And the Hamiltonian is an operator which is something that the observer outside can measure, because the observer outside, or at least the observer outside can measure moments of the Hamiltonian. Maybe the observer outside can't measure the Hamiltonian as a complete operator, but can measure correlators of the Hamiltonian, because in gravity, as we have used many times, the Hamiltonian is just given by the behavior of the boundary metric. And so if you quantize the metric and then measure correlators of the metric, that contains information about the energy. And the mirror operators had the property that they don't commute with the Hamiltonian. This is what sometimes colloquially referred to as the fact that the particles behind the horizon have negative energy. So this commutator in particular has the wrong sign from what a usual annihilation operator would be. But it's just something that naturally comes out of the way we, if you just gauge fix the field carefully or dress the field carefully to the boundary, and then do an analysis of large diffeomorphisms, you will find this commutator. So in any case, we have this commutator, and so we should not have that if you have a conserved, the Hamiltonian or another conserved charge, we should not have that the commutator of these mirror operators with this conserved charge just vanishes or appears to vanish. Rather, you should find that the commutator is of correctly this form. And there were proposals which suggested that you might want to make the commutator vanish, but that those run into trouble. And so it is important that this commutator not vanish. And so I now want to explain how one gets around that. So the idea is as follows. You see, we had a state psi, which was our equilibrium state. And then on the equilibrium state, we can now consider additional states that are obtained by taking this Hamiltonian and acting on the state psi. So we can consider the state h psi, h squared psi, h cubed psi, and so on. In general, these states are all independent from the original state psi. It may not be the case that these states are independent. It may in fact be, and this construction that I'm describing works also for energy eigenstates or something that's very close to an energy eigenstate, in which h psi is almost close to psi. But that's a simple extension of what I'm going to describe. And so I won't do it explicitly, but you can check later that, this construction I'm describing will work also for that case. But let me just point out that for a generic state, if you consider h psi, that is not the same as psi. And the reason is that, psi is some linear combination of energy eigenstates taken from some band. And in general, these coefficients are non-zero. And so if you take h psi, that gives you some different state, which has different coefficients, where these coefficients have been multiplied by ei. And similarly, if you take h to the n, that gives you e to the n. You might want to normalize these states. So it's perfectly reasonable to normalize these states by dividing out by an overall factor of the expectation of the energy. But we're not interested so much in the normalization right now. I just want to point out that all of these states are linearly independent states. So they are distinct states. It's important, of course, that when we consider these moments or these powers of the Hamiltonian, we put a cutoff on n as well. So we put a cutoff on n, and that cutoff is not, we don't need to specify it, but once again, it's important that this cutoff ensures that, it's much smaller than s. Okay. So we have, we put a cutoff, which is some order 1 cutoff, and this cutoff is much smaller than the entropy. And that ensures that, we are looking at moments of the Hamiltonian, but not at very high moments of the Hamiltonian. Okay. So we now have a set of little Hilbert spaces, which we can construct on top of each of these states, h to the n psi. So I can define a little Hilbert space, which I can call h psi n, which is simply the span of the simple operators acting on h to the n psi. So rather than acting on the base state psi, I take the simple operators and I act on h to the n psi. And for every value of n going from n equal to 0, which was the original little Hilbert space, up to some higher value of n, up to this cutoff, which is not specified, but there's some cutoff, which ensures that, I don't take too high powers of h, I get a little Hilbert space. And then the idea is, and as I said, these little Hilbert spaces are all linearly independent. They're all linearly independent because, because of what we have here. For generic coefficients, AI, EI is not related to AI. And it could be the case that, there's some special choice of coefficients, in which case this construction will still work, but we won't deal with that special case now. For the generic case, these spaces that we get are all linearly independent. And therefore, we can define on the direct sum of all of these little Hilbert spaces, the mirror operators to act as follows. So the rule is that we define the mirror operators to act in this way. So we define this to just be a omega dagger h to the n psi into the factor of e to the minus beta omega by 2. And similarly for a omega tilde, and of course for any other polynomial. But notice what we have done here. And in general, for any operator, the mirror of the operator is defined in the natural way. But I want to point out, having written these formulas, a feature of these formulas. Remember that when we didn't have this factor of h to the n, the rule was that you take the mirror operator and you float it all the way to the right next to the state, and then you convert it into an a omega dagger, right? So this is a set of linear equations for this operator a omega tilde. If I take this to define a set of linear equations for the operator a omega tilde, this set of linear equations has a solution by the no annihilation condition that we wrote down last time. It has a solution because, you know, this operator AMHN never annihilates the state psi. And so we, you know, you can use this as there is an operator a omega tilde that satisfies these equations. Yesterday, I wrote down an explicit formula in terms of some metric on the space of states. You could easily generalize this metric to this larger space of states, which is not just you know, AM acting on psi, but AM with these factors of h to the n acting on psi. And you could write down an explicit formula for a omega tilde. But the important part about these rules that I'm specifying is that I have not moved the a omega dagger to the right of h to the n. Rather, it is still sitting to the left of h to the n, and it is acting on the state that way. So, you know, this is also a natural rule, because all of these states h to the n psi are also equilibrium states. So there is really nothing that, you know, that distinguishes the equilibrium state psi from the other equilibrium state h to the n psi. And, you know, you could have started with, say, the state h psi or h squared psi. And then the rule for the mirror operator would obviously have been that, you know, here's the base state, and you move the mirror operator all the way up to the equilibrium state. And there you just stop and you convert it into an a omega dagger. Okay. So this rule is distinct from the rule we had without this factor of h to the n. And the reason it is distinct, of course, this is designed to give you the right commutator, but it's also, there's a good physical reason for it, which is that these states h to the n psi are themselves good equilibrium states. They're as good equilibrium states as the original state psi. And therefore, you know, it doesn't make any sense to try, you know, you could have just thought of this whole thing as a single state, done the construction about that, and then this is the rule that you would have got as it's written here. I want to now check, I want to show you explicitly that this gives you the correct commutators. Is there a question?
Sorry, can I ask a question? So, so the space hn psi that you've defined, so that's sort of like the time evolved versions of psi, right? So if you wanted to think of psi first and you wanted to think of its time evolved version, it would be some combinations of states in hn psi.
Yeah, you could think of its time evolved versions. That's one way. I mean, you'd have to take some derivatives, but okay. Yeah, it's indeed true that h to the n t to the n psi. Yeah, but you know, we're not going to do time evolution for too long a time. So this is really, yeah, you could think of it as some small time evolution of psi, if you like.
Right. And then there's some cutoff on how much you can evolve on. Exactly.
Not very much. Right.
And then this statement about the mirror operators can also be thought of as a state. That's, you know, the mirror operator acting on the boundary state is sort of local on that state. It doesn't.
Right. So if you time evolve the equilibrium state, you get another good equilibrium state, and the mirror operator acting on that you know, and then you just naturally define the mirror operators on that new equilibrium state, and you would get this rule. Exactly.
Right.
Okay, I have a question.
Yeah, sure. Yeah.
Are these little Hilbert spaces disjoint, the ones for different values of n?
Yeah. So right now they're linearly independent. You know, it's true. It's of course true that there is an inner product here. So if you take like h squared, you could get an inner product. But what we need in order for this to be consistent is that you never have am h to the n psi. You know, you sum over any value of m and n and put any coefficients. You never want this to be 0. And this is generically the case. So all we want here actually is not, we don't want them to be disjoint in that they're not, if by disjoint you meant are they orthogonal to each other? They're not orthogonal to each other. But they, you know, they do give you in the generic case a set of linearly, all of these vectors are linearly independent, even though they're not orthogonal. And you can do.
I'm just a bit worried, for example, in the first rule you wrote there, if h to the n psi belongs to the little Hilbert space of psi, then that itself can be written as simple operator acting on psi. And then the rule that we wrote last time would tell me that you should shift the a all the way to the other side.
Correct. So indeed, it's true that we need this condition, which is that you know, h to the n. So if it was the case that h to the n psi itself was like some simple operator acting on psi, then we would be in trouble, and this condition would get violated. But you know, notice yeah, because you know you would choose like CMN, like CQ0 to be something, and h and then you choose am to be the identity. So you see this condition would get violated if this happened. But for generic states, you know, it is indeed the case that h to the m psi is not the same as any other simple operator acting on psi, because you know it's very hard. This is not a special condition. If you take, you know, if you take like we've added, now we have some simple operators, and to this we've added some Hamiltonians, and the Hamiltonians do something, and some other operator like a omega does something else. And in general, it's very difficult to take some coefficient of just the Hamiltonian and some simple operator, some low power of the Hamiltonian, and make the state vanish. So you know, this is by the same argument that we had yesterday. You have a small set of operators which now include some powers of the Hamiltonian, and by acting on them, you can't make the state vanish. If it did happen that, you know, you had some rule of this kind, then you know, things might work or they might not work. You know, one simple case where things certainly do work is if you have h psi is equal to E psi. So if you just consider an energy eigenstate, in which case this AQ is just the identity, then in fact the construction I'm describing just works automatically. But if you had some more complicated relation where h to the n was like some other simple operator, then this construction would not work. But that would only be true for a very small set of states, for a measure 0 set of states. And those states, you know, might indeed have firewalls, because it would tell you that if you time evolve the state a little bit, you know, it's the same as acting with some other operator in the state. And such a state, you know, there are some measure 0 states which have this pathological property, but the construction would not work on such states.
Okay, thank you.
Great. Okay, so very good. So I want to check explicitly that with this rule, we get the right commutator. Let's do the check. Just take a new slide. So, you know, let's compute a omega tilde on h. And of course, you can do this for a omega dagger. So we just write this out. I'm just going to do some algebra, but the algebra is really very trivial. So you can just do it alongside. So here I just expanded out the commutator. And here there are two terms here. One term here is a omega tilde into h a n psi. And then we have another operator which looks like h a omega tilde times a n psi. Okay. Now, when we look at this operator, this one here, we can, in fact, you know, even though this operator looks like, you know, this operator has some component which is in the little Hilbert space built on top of h psi, and some component which is in the little Hilbert space that's built on top of psi itself. And in order to be able to figure out how the mirror operator acts on h a n psi, we should disentangle or you know, separate those two components. So we just use the fact that HAN is given by minus IAN dot, where AN dot is another simple operator that is the time derivative of AN. So if we use the description of simple operators that we had yesterday, where we were taking the simple operators to just be polynomials in the modes of the generalized free fields, then this, this commutator of the Hamiltonian with one of those modes is just is another one of those modes. So it's a linear combination of some of those modes. If you had a omega plus a omega squared, you commute that with the Hamiltonian, you get a factor of omega in one case, a factor of 2 omega in the other case. And therefore, for the set of simple operators that we had, you see that the commutator of the Hamiltonian with the simple operator is itself another simple operator, which I'm writing as an dot, but really, when you're thinking of modes, it's just some other linear combination of the operators that comprise an. And so we use this, and we can write this expression here as a omega tilde into HAN psi plus a omega tilde into an h psi. And then we have a minus h a omega tilde into an psi. Okay. And then we use this fact here. So this looks like an a omega tilde into an an dot psi with a factor of minus I. And then here we write this as an into an a omega dagger h psi into an e to the minus beta omega by 2. So this came from this term. This came from this term. This is the rule that I had. And this last term we can write as minus h an into a omega dagger psi e to the minus beta omega by 2. Okay. So this just came from applying a omega dagger on this state. Okay. Okay. So I hope this algebra. There are a lot of terms, but there's really not much that's going on in this algebra. Now, let me copy this expression. You see, on the first term, I can once again use my rule for the tilde. So this looks like an dot times a omega tilde psi. Okay. And let me just take the second term first. So this term that I have here. This term also looks like minus h commutator an, okay, plus an h let me just write the term separately, plus an minus han minus anh. So I hope I got my algebra correct now. Okay, I think I sorry. Excuse me. Minus han and so I should have minus an. Thank you. Okay, great. Okay, so I think I got my algebra correct. Sorry for messing that up. There's a commutator of this term I just copied. Okay, this term I just moved the a omega tilde here. So this term just comes from here. Then I have this term which I have moved here, and then I've just taken the middle term, and I confuse myself right now in writing it as a commutator plus another term. But now that this is done, notice that this term is also this commutator is minus of IAN dot, but this is going to, there's a factor of e to the minus beta omega by 2. But notice that this term is going to cancel this term. Because this term, I could use the rule and write this as a omega dagger with an e to the minus beta omega by 2. And so these two terms are going to cancel because this is also going to give you an an dot. So this and this cancel, and we are left with only this term and this term. So the only two terms that we have left are an a omega dagger h psi minus an h a omega dagger psi, and the whole thing is multiplied with an e to the minus beta omega by 2. Okay, so the algebra is a little bit messy, but it's actually quite simple if you just use the fact that the commutator of the Hamiltonian with a simple operator is another simple operator, and then you just apply the rules that we had previously, you will find that everything cancels and you are left with this simple expression in the end. Okay. But this expression we know how to evaluate, because you see what appears here is just the commutator of h with a omega dagger. This is just the commutator of, or rather the commutator of a omega dagger with h. And so this is something which is something that we know, and we just use the fact that this is, this is equal to minus into omega into an into a omega dagger into psi into e to the minus beta omega by 2. But now this we can write as we had earlier as minus a omega into a omega tilde into an psi. Because the action of a omega tilde on an psi would just have given you this a omega dagger times e to the minus beta omega by 2. And here I just have a factor of minus omega. So the trick was to write everything in terms of ordinary operators, as I did here. We do know the commutator of h with the ordinary creation operator. And so now we have found an expression which evaluates the commutator, and we have got back this. Okay. Remember, where we started from was this expression. This was what we started from, and we did some algebra, and we found that this was, so where we started from was this expression. We put another equality, and what we have found is that a omega tilde commutator with h is minus of omega a omega tilde, which is the same as the statement that h with a omega tilde is omega of a omega tilde. And so as advertised, if you use these rules that we have written down and you do a little bit of algebra, you find that the commutator of a omega tilde of these mirror operators with the Hamiltonian works out as was expected. Okay. So this is a check that the expression that we had with the conserved charges, the improvement of the mirror operators that we did, does give us the necessary correct commutators with conserved charges. We did this example for the Hamiltonian. One could do this example for other cases with other conserved charges, and it would work out, except in those pathological cases where this no annihilation condition was not satisfied. If that is not satisfied, then the state is a state where the construction of the mirror operators doesn't work, and you can see explicitly that you cannot find operators behind the horizon which have the right correlators with operators outside the horizon, and that suggests that this state does not have a smooth horizon. Okay, so this is all I wanted to say about conserved charges. Is there a question? Yeah.
Yes. So just in the last page you wrote down that the commutator of Hamiltonian with the AM is also belongs to the algebra, the simple operators, and yes. And we can see this from the choice we have. In terms of A and A daggers, but does it follow directly from the conditions of the simple algebra?
You're right that in the conditions that we wrote down yesterday, we didn't explicitly write that the commutator of H with the simple operator belongs to the algebra, and we should in order for this to work, that should be a condition that we should add on, that it's not just the simple operator, but also at least their time derivatives are also part of the algebra. So that's a condition we should write down. Maybe I should say that the conditions I wrote down yesterday for simple operators have never really been worked out precisely. I only wanted to say that in all the examples or in the literature that you'll find, everything is always done by just taking modes, these polynomials of modes. So nothing is ever done with some more general set. I only wanted to say that it might be that a more general set of simple operators is useful, and so you should think about that set. And I was trying to write down some conditions that are necessary but not sufficient, as you point out correctly right now.
Okay, yeah, thanks.
Okay, great. So the next point I want to discuss is the issue of near equilibrium states. Okay, and this is related to what's sometimes called the frozen vacuum problem. So the issue here is that so far we have defined these mirror operators on states that we call equilibrium states, which are states where these expectation values were all time independent. But it cannot be the case that this definition that we have is the correct definition for all states. And let me give you an example to show why it cannot be correct. So let's call psi ne, where this ne stands for near equilibrium. Let's call this, so this is a unitary operator acting on the state psi. And this unitary operator is something that might well belong to the set of simple operators, or might be something which is very well approximated by something that lives in the simple operators. It might just be a simple unitary, maybe e to the I a omega dagger. So some a omega dagger plus a omega, something that just creates some small coherent excitation on top of the state psi. And I'm just calling this state psi ne. Okay? This state, if this original state is in equilibrium, then you can check that no simple operator you can write down, apart from, of course, the Hamiltonian, which we're not considering here, but we're considering some other excitation which is made up of these simple operators. No other excitation you can write down will give you another state which is an equilibrium state. And the reason for that is that the conditions that we put on these equilibrium states were very strict conditions. We demanded that these correlators be time independent to very high accuracy. And if you explicitly put in an excitation in terms of this U, then of course, the time at which you put in that excitation breaks the time translational invariance of the state. And the new state is not an equilibrium state. Okay? Nevertheless, because we are considering simple excitations, we can think of it as a near equilibrium state, although it is not an equilibrium state. Okay? Now, if somebody just gave you this near equilibrium state, and we tried to ask what is a omega tilde on psi ne. Okay? Now, let's say somebody said, well, we will just define, I don't know about your equilibrium condition. I'm just going to define this to be e to the minus beta omega by 2 into a omega dagger into psi ne. Okay? Let's say somebody, this is not a true equation, but let's say somebody did this. Okay? Then it's clear that this definition is wrong, because if you use the original definition that you had on top of the equilibrium state, then you would find that you would get something different. Which is not equal to what we have on top. Okay? And it's not equal to what we have on top in general, because it may happen that a omega with u or a omega dagger with u is not equal to 0. And therefore, if someone were to come up with a definition that disregards the issue of whether a state is in equilibrium or not, it is clearly a definition that would be wrong, in that you can see that it would be inconsistent with the original definition that we put in on top of the equilibrium state. And so it is important that this definition cannot be the right definition for these near equilibrium states. There's another way in which this is sometimes stated in the literature, and that is that you can think of the following picture rather than writing these equations. You could think of the following picture, where you have a black hole, and the black hole was created some time back. But after the black hole was created, I threw in another shock wave. Okay? So this is my unitary U, which is an excitation inserted after the black hole formed, or well after the black hole formed. If I use this kind of a definition, this wrong definition that we have here, then the mirror operators would not respond to this excitation at all. Right? They would, in particular, let's say you computed the correlator of A omega tilde with A omega, this correlator would not respond to the presence of this excitation at all. It would just, ignore the presence of this excitation. So just to be more clear, here is an infalling observer who here has to travel slightly superluminally because of the way I drew the diagram. But if you draw the diagram correctly, the infalling observer is on a time-like trajectory and doesn't have any space-like parts. But the point is that the infalling observer here is measuring a correlator involving A tilde. Okay. And it's, you see that if you were to use this wrong definition, then the infalling observer would never see the shock wave. So you could throw in whatever excitation you like, and if someone were to say that I think this is the right definition, then this excitation would just not affect the horizon. And you know that in some cases the horizon should be affected. It should not just behave like a featureless horizon in all cases, and that's why this a definition which corresponds to this, a construction which uses this, wrong formula, suffers from what's called a frozen vacuum. So how do you fix this problem, right? Of course, if you have the original equilibrium state, you have this state psi, then of course, you know how the mirror operators are defined, and you also know how they're defined in psi ne. But let's say the infalling observer, our observer here, just happened to find a certain state which was presented to the observer. So just, let's say somebody just gave you this state psi near equilibrium and said, now tell me what is the experience of the infalling observer. How do you find a construction which avoids this frozen vacuum problem? So the idea of doing this is the following. You see, if you're given psi ne, we can back calculate psi and u, so that psi ne is equal to u psi. How can we back calculate the base equilibrium state and u? Well, we just look for a unitary v. So we just look for v, so that v dagger psi ne apt is t independent. So if you're given a state in which the correlators that you have are not time independent, then you can ask, what is the unitary operation I would have to do to the state in order to make the correlators time independent? Of course, it could be that there is no such unitary operation in the set of simple operators, in which case the state you're presented with is not a near equilibrium state. But if the state you're presented with is a near equilibrium state, then by searching in the set of unitaries made out of simple operators, you can ask, what should I do to the state in order to make it time independent? And you can check that only v equal to u works. And the reason for that is that, let us say we were to choose v is equal to uw dagger. Okay. Then you can see that, let me just copy this part. if you take V equal to UW dagger, then you find that the expression above will become psi, and you will get an additional factor of W, and you will get an additional factor of W dagger APT, where this psi is the base equilibrium state on which you had acted with this U. So if you were to take this V to be not U, but U times some other unitary W, then you would find that this expression would become this expression. But you can check that if you have some unitary W, you can always find some operator. If this W is made out of simple operators, you can always find some other operator that doesn't commute with what makes up W. And if that operator doesn't commute with what makes up W, then this expectation value will not be time independent. So, and the reason this is working is because the condition on an equilibrium state is really a very strict condition. I mean, it's a strict condition in that it's met by generic states, but in general, if you try and excite a state, if you hit a state in thermal equilibrium, then it is not in thermal equilibrium. So if you excite a state with a simple operator, you can also use simple operators to detect that the state is not in equilibrium. And therefore, you have to choose V is equal to U. And so if we are given, the upshot is that given psi NE, we can determine a V so that psi NE, a unique V, is T independent. Okay. So this is the upshot. And as I just explained, if there's one solution for V which works, and if you try and take a different solution, then the solution would not work because of the physical argument I gave, but you can also try and make a more rigorous mathematical argument. Okay. So
yeah, I have a question.
Yeah, sure. Yeah.
Okay. So in writing near equilibrium state, we took U as a unitary simple operator. But can you give an example for such a U? Because exponentiation of Hermitian operator won't work in this case.
Yeah, good. It will work actually. So you have to be a little bit careful. You're right. When we put a cutoff here. So I don't know if you're asking about the cutoff. This is an example of such a U. This is arbitrarily the cutoffs that we put were cutoffs that we put at order, to ensure that you never had like exponentially large number of operators. But this is pretty well approximated by a polynomial, you see, because this is a simple operator, right? So this is actually, for all effects and purposes, this is a simple operator. So if you're asking, do you have something, can we come up with something which is mathematically more rigorous, where, you include these kinds of operators as well? You can. And you're right to point out that when we just use polynomials, we didn't quite include these exponentials. But there isn't really a difference, because you can always use a polynomial and expand it this way. If you put like a huge coefficient here, then it would not work. And if you wanted extremely high accuracy, like if you wanted arbitrarily high accuracy, then this expansion on the right hand side would not work. But at the level of rigor we are working, which you're right is not extremely rigorous, we are not making it, we will treat this as a simple operator. So this is an example of a unitary which will create an excitation. I don't know, did that answer the question?
Yeah, but this equality takes care of the cutoff, right? I mean, in the summation.
Yeah, it breaks the cutoff. But if you put a cutoff, this cutoff, the terms that you neglect are very small. So let's say somebody told you I had a cutoff, right? So let's say instead of U, I actually could only write down from I equal to 0 to some D. Okay. But this D can be pretty large. This D can be, this D doesn't, it must be much smaller than e to the s. But maybe you could take it to be like, e to the square root s or something. And then the terms that you neglected are extremely small terms, right? Because everything is here is divided by some n factorial. So when you write down an exponential can be approximated very well by a polynomial. And you're right that you can't take the polynomial to be arbitrarily high order, but to, within the purposes of low point correlators, every correlator that involves this exponential can be approximated by a correlator of a polynomial. And then you're right, there are some cutoff dependent issues, which no one has ever worked out carefully, which one is assuming are not important, but maybe they're important in some way, and we're not, no one has been careful enough to work out these issues. But the assumption generally is that you should be able to approximate a unitary operator as a polynomial, and this cutoff is much smaller than s, than e to the s, but it's high enough in order to allow this approximation to be a good one.
Yeah. Okay, I understand. Okay, thanks.
Okay. Great. Okay, great. So for such states, yeah.
Can I ask you to repeat?
Yeah, sure. Yeah.
The last argument that we use to say that if we include a w, a unitary w, that correlator is not time independent.
Yes. You want, so you see, if you
can just repeat that part.
Yeah, go on, please. Sorry, maybe I interrupted. Yeah.
No, I was trying to clarify my question. My question is just if you can repeat that very last argument.
Yeah. If you take an insertion of this kind, like if you insert some simple operator, then in general, that simple operator creates, so let's say you inserted an operator of this kind. So if you had, if you had an equilibrium state and you hit it with an operator of this kind, then this operator creates some excitation, right? So if you act on this with e to the minus IHT, then this gives you some phases. It doesn't keep these phases constant. So it gives you some phases, and it's very hard to find an operator where these phases are exactly 0 to the accuracy that is required. You might try and take a omega, smear it a little bit, multiply it with a omega dagger. But the equilibrium state is really a very delicate condition where you want these correlators to be time independent to an exponentially high accuracy, and it's very hard to take one of these simple operators and find something that has that commutes with e to the minus IHT. So if you write this psi, so you could write we'll give you some phases, and as a result, if you compute the expectation value of something else, say a omega minus a omega dagger, put e to the IHT, put the same thing. Then this will start depending on t. It will start depending on t because of the fact that you have this excitation here, and so this starts depending on t. It's another way to say it is that when you insert such an excitation, you generally give an expectation value to some operator in this small algebra that has non-zero energy. If in the absence of such an excitation, the only thing that can have a good expectation value is something that has exactly 0 energy. So it's basically 1. But once you insert like one of these excitations, then you start giving an expectation value to operators which have a non-zero energy. And that's what puts you in trouble. That's what breaks the time independence. So once again, if you look at this at the original paper, this was defined. This is done a little bit more carefully, but this is the intuition that goes into the argument for why once you excite an equilibrium state, you don't remain any longer in an equilibrium state.
I understand. Thank you.
Okay, great.
Just as a comment, but since we earlier showed that typical states are dense and so on, wouldn't you naively expect any non-equilibrium like perturbation can be accessed from multiple typical states? And psi is a typical state here.
But you might need to add up a very large number of typical states. So you would need to take a linear combination of many typical states. These near equilibrium states are atypical states. They are states which are not typical. They're
right. So I would have thought like there are multiple typical states or sums of typical states which are close to them.
Oh, sure. You can take sums of typical states and you get a non-equilibrium state. Yeah, I agree. There are specific sums of typical states you can take.
But that's again a typical state, right? Sums of typical state.
No. The set of typical states clearly can't be closed under arbitrary sums, right? Because if you took arbitrary sums, then you would generate everything. So the set of typical states is something which is some set which clearly is not closed under arbitrary linear combinations. It can't be.
Okay, thanks.
Okay, so for such operators, we find the following. For such states, we define the mirror operators in this way, as a omega tilde acting on am on psi ne is am e to the minus beta omega by 2 into a v a omega dagger v dagger psi ne. So notice I have now inserted an additional factor of v and v dagger. And what these factors do, this factor of v dagger strips off the original unitary that created the excitation, and it moves it to the left. So this is consistent with the original expression that we had, which was that so these two expressions are in fact the same expression, this one and this one, even though this one is written in terms of a construction on a near equilibrium state, and this one is written in terms of a construction on an equilibrium state. But notice that this factor of v and v dagger that we have above precisely ensures that these two are consistent. Okay? So this ensures also that the mirror operators do not suffer from a frozen vacuum problem. Okay. Okay, so this is the second point I wanted to make, and this is in some sense an important issue because it keeps arising many times in the literature. Even though in some sense, I should say that having to insert these unitaries by hand, so these unitaries that we have here, kind of makes the construction a little bit more ugly. In fact, there was yesterday a question about how these things work within Tomita-Takesaki theory. One reason let me just copy this just to focus on this expression. One reason I didn't present things in that way is that this Tomita-Takesaki construction works nicely if you're in equilibrium states, but it does not work so nicely if you're in these near equilibrium states. In particular, this Tomita-Takesaki construction of these operators is not able to correctly give you these factors of v and v dagger. It gives you some wrong factors. It gives you some factors, but gives you some wrong factors. And not, at least, if you just take the Tomita-Takesaki construction as it is usually done and try and define the mirror operators in terms of these, in terms of Tomita-Takesaki theory, you will not find these correct factors of v and v dagger for near equilibrium states. And so in some sense, this ensures, you need to have these factors in order to ensure that you don't have a frozen vacuum problem. But it kind of is aesthetically a little displeasing that you need to insert these factors of unitaries for near equilibrium states. And it would be very nice if someone could generalize this construction and find some, formula like this Tomita-Takesaki formula that just works. That just works in general and automatically generates these factors of v. So the procedure I described right now was, you take the near equilibrium state, you calculate some unitary that makes everything time independent, and then you put in that unitary in terms of the definition. And it would be nice if there was like some more natural way of getting this, which as far as I know does not exist. And it's something that keeps getting discussed several times in the literature. Most recently, for example, in this paper by Jaffris and Lamprou, but many times. And so if you look at the lecture notes, the printed lecture notes, there are some references that will direct you to more discussion on this issue. Okay, so very good. So yeah.
Sorry, can I have one question?
Yeah, sure. Yeah.
So if we have factors of the Hamiltonian, so if you had like the mirror operator with some factors of Hamiltonian with these non-equilibrium states, then what does the action look like? Is it the same as earlier?
Right. So you should always define it in order that it works consistently with the original definition, right? So you should always define it so that so you have like if you have am h to the n, yeah. So it'll be more complicated, but if you have you should probably, yeah. So if you have some operator of this kind, then you should always define it so that yeah, so you have to be a little bit more careful about how you commute things. So you're right, you'll have to write down a little bit something which is slightly more complicated. So one option is you define your little Hilbert space by acting with this unitary or in terms of the original equilibrium state. But if you define it this way, here the definition is clear that you have an additional edge a omega tilde is equal to omega a omega tilde, and you need to incorporate this commutator when you make this definition. So there are various ways you could do it, but you're right, it would be a little ugly to write it down explicitly. That if you just try to move the a omega tilde here, that would not work, and you would either have to move the edge to the end through on this side, or you would have to incorporate this commutator in moving these things here. But it can be done, but you're right, it would look a little ugly if you were to write it down explicitly. I hope that answers the question.
Yeah, thanks. Because I was just wondering that it just can't be the definition that was earlier, because then that would
it can't be a definition that is earlier. You can't just move it to the left and leave it here because there's an edge to the end, which is there's a u after that. Correct. That's
yeah.
Great. Okay, so far we've constructed these mirror operators in specific states. Okay, we've discussed them in a fair amount of detail, and we've constructed them in some specific states. But so far, because we have constructed them in some specific states, this construction is not what we have done so far. So we will talk is not what is called state dependent. Okay? The reason it is not called state dependent is, remember, what did we do? Right? We said, here is some state, right? And we define these operators, and I defined some other operators, which were I defined some other vectors, and then I said, I'm thinking of the operator which looks like UMVN, and this is what I was calling my A tilde omega. Okay. Now, this is not a state-dependent operator. This is a perfectly well-defined operator on the whole Hilbert space. It just so happens that it does not give you the right correlators if you insert this operator in a state which is not the state psi. Okay? But this operator, as it is written, is not state-dependent. Okay? So I want to emphasize, and this is something that sometimes might cause confusion. For instance, let's say I even write down, forget about these mirror operators. Let's say we write down the projection operator, which is psi. This is not what we will call a state dependent operator. If I pick a particular psi, it so happens that p psi on psi is equal to psi. And if I pick some other state psi prime, I might get 0. Right? So if I just say, here's a projection operator, this projection operator treats some states very specially, it treats the state psi specially. But if I told you what psi is, or I said I want to define a projection operator on a particular psi, then this is an operator that we use all the time. This is not a state-dependent operator. It does treat the state psi differently from the state psi prime, but that doesn't make it state-dependent. It's just defined globally on the Hilbert space, as is the operators we have been discussing so far. Okay? But what is the problem with the operators that we've been discussing so far? Okay? So let's say we have another state. And let's call that state psi2. Okay. In fact, if you'll permit me, I'll go back and I'll call this psi1, and I'll put an A omega psi1 here. So this is the operator that we constructed on the state psi1. And let's say we have another state which we call psi2. And we look at this correlator. So this is, maybe it's an equilibrium state. Okay, so we don't worry about the issue with near equilibrium operators, but it's just an equilibrium state. And let's say we now ask for A psi1 tilde omega A omega psi2. Clearly, this is likely to give you something which is exponentially suppressed, whereas what we want is something different. What we want is e to the minus beta omega by 2 by 1 minus e to the minus beta omega. Why does it give you something that's exponentially suppressed? Because you just look at the definition of the operators that you had here. Look at this definition that you had here. And this definition is a definition which works for an operator in the little Hilbert space constructed around psi1. And it annihilates something that is orthogonal to the little Hilbert space that is, that is orthogonal to the little Hilbert space constructed around psi1. So this order minus e to the minus s by 2 is like the order of the inner product of psi1 and psi2. It's the fact that if you take a vector or an which lives in the little Hilbert space of psi1, and you take the inner product of that with psi2, you get something that's exponentially suppressed. And if you look at this definition, this explicit formula that we have here, then this explicit formula clearly just annihilates vectors which are orthogonal to the little Hilbert space of psi1. And if you were to act with this operator on psi2, you would get the inner product of these operators with psi2, and that would be exponentially suppressed. Okay? So you see that this operator does not work I'll use the term work, but really, a psi1 does not work in psi2. Okay, I hope what I'm saying is clear. It means it does not have the right correlators if you insert it in simple correlators about psi2. But rather than writing that every time, I'll just say it does not work in psi2, in that it does not give you the correct expectation values for simple operators about psi2. Okay? So what do we do? Okay, so we have some construction, and we have something that was about psi1, and it doesn't work about psi2. So here's one thing. We could say, well, good, let me generalize things to a psi1, and let me also do a construction about psi2, and let me add together a psi1 plus a psi2. Okay? So this is constructed in h psi2. So I have the little Hilbert space about psi2. I can do exactly the same construction that I did about psi1. And now I have an operator, which is the sum of these two operators. This operator has the nice property that it works in psi1 and psi2. And why does it do that? Because if you compute correlators of this operator in psi1, then this operator just doesn't count, because it just doesn't click if you insert it inside psi1. This operator just doesn't click if you insert it inside psi2. So this sum operator works both in psi1 and in psi2. In fact, it also works in any linear combination of psi1 and psi2. And the reason for that is that if you were to compute, sorry, I should have written mirror operators, sorry. If you were to compute the correlator of this mirror operator with an ordinary operator in where psi was equal to psi1 plus psi2, then you would find two terms. You would, of course, first find the term mod of a squared. And in this term, only this operator psi1 would count. Then you would find a term which had a mod of b squared. In this, only this operator psi2 would count. And I'm dropping exponentially small terms here. And then you might have thought that, maybe you would get cross terms. So you might get one term which looks like a star b, where you have cross terms. But these cross terms can never count. And you would have another cross term which would look like. But you see that both of these cross terms, and there are also some other terms which look like AB star, but you see that these cross terms will never contribute, because you have a tilde psi1, and here you have the state psi2. So you have the inner product of something in the little Hilbert space of psi1 with something in the little Hilbert space of psi2, and that will be very small. And same here. Okay. So this whole thing is in the little Hilbert space of psi2. You're taking the inner product with psi1, and this will vanish. And therefore, I can also cross out these two terms, and I only have what is left on top, only these terms. And these terms are indeed what you do expect if you take a superposition of two states. If you take a superposition of two distinct, black hole microstates, you do expect that in fact, that superposition behaves like a classical mixture in that you don't see interference between those two terms for a small superposition. And that is what you see here. And so that tells you that this kind of a mirror operator works in psi1 and psi2 and also works in a linear combination of psi1 and psi2 because linear combinations behave very simply. So you might say, aha, very good. Let me now just keep taking larger and larger sums. And by doing that, I will construct the mirror operators so that they just work very generally. So let me just write down, this A omega tilde about psi1 and psi2 and psi3. And let me just keep going till I have got like psi n. And I can take this n to be e to the s. So when I do that, I will get, I will take a basis for the Hilbert space. I'll take psi1 to psi n to be a basis for the Hilbert space. And I'll construct these mirror operators about every element of the basis. And then I'll just add them up. And I'll use the argument I had previously. And the argument I had previously will tell me that the mirror operator will now work correctly in all states. I'll have something that works globally in all black hole microstates. But you see that when n reaches e to the s, which is what you would need to do in order to construct a basis, you might imagine that you've got you've succeeded, or and we found something that works correctly in all states. But in fact, what has happened is that you have ruined even your original construction. And the reason for that is that if you take psi1, let's just forget about inserting it in arbitrary states. Let's take this operator that we have, and let's just insert it back in the state psi1. A omega dagger. So let's just compute this in the state psi1. And you will find one expression which will come from the operator. So this is now my A omega tilde. You'll find one expression which comes from the operator about psi1. This is what we want. But now you will get e to the s terms which will come from different operators. So we did argue earlier that these terms were small, but now I've got e to the s terms. And if I have e to the s terms, then there is no reason that these terms should be small as well. So these terms will now not be small. And now we are in trouble because we found that even in the original, in one of the states that we originally constructed things in that was included in the sum, when we reinsert this huge sum back into the original state, we find that it does not give us the right correlators even in that original state, because all these other operators you added can now give some contribution. The sum could be large, and all these other terms could give some contribution that might mess up even the correct answer that you're getting from one term. Okay. So therefore, we can't just add up these mirror operators by constructing them in different states and get something that works in the global Hilbert space. At least naively, you can't. Okay. So let me just draw a picture of how this works. So the picture is as follows. You see, here is a big Hilbert space. And in this big Hilbert space, we can write down some smaller Hilbert spaces. So this is H. This is H. And here are our little Hilbert spaces, which we'll call it psi1, H psi2, H psi3, and so on. Okay. Now, provided we pick a small number of little Hilbert spaces inside the big Hilbert space H, we can define mirror operators in a way that these spaces don't overlap. So we can define an operator here, which is A psi 1. We can define something here, which is A tilde psi 2. And all of this is consistent. We can take the sum of these operators and we can get something that works in the sum of the little Hilbert spaces. But if you start trying to expand the ambit of these little Hilbert spaces so that they cover the full Hilbert space, then you start finding that there are places where these things start colliding. And then at the points where they collide, you have potentially some difficulty. Now, this doesn't mean that you cannot find, for anything an operator that works correctly, but it does tell you that, when the little Hilbert spaces start colliding, okay, we need these A tildes to mesh together smoothly. Okay. Now, it might happen that, the operators A tilde that you have do automatically mesh together when these little Hilbert spaces start colliding. I hope what I'm saying is clear. We have these little Hilbert spaces, we define these operators. Now we are trying to cover the whole space, and then these Hilbert spaces start colliding. And it may not be the case, it may or may not be the case that these operators agree at the points where these little Hilbert spaces intersect. And it may happen that they do agree, or it may happen that they do not agree. In fact, the conclusion of the paradoxes that we discussed 2 lectures earlier, the paradoxes for large black holes, they imply that no global mirror operator exists. So, whatever we do, we might try and modify the definition to make something work, or make these operators mesh together well in the interface. But the paradoxes that we found tell us that you will never succeed in, or we will never succeed in finding a mirror operator that works for all states. Because we argued, that was the point of the paradoxes. It was that you cannot find something that works for typical states. So the mirror operator construction that we defined works for some states, and you could start extending it so that it works for some combination or direct sum of little Hilbert spaces, but you cannot find a single operator that works for all spaces. Okay? So no single operator can simultaneously work about all typical states. Okay. So now what do we do? So we have a few options. One option, of course, is that
can I ask one question?
Yeah, sure.
Yeah. So so I just wanted to ask, if you wanted to have the sum of different mirror operators, right, and try to see if that works, and we saw that doesn't quite work because it has expectation values in these other states,
right,
and not just in psi 1.
Right.
But if we have some, if we know what these expectation values look like, then we could presumably take a psi and sort of smear it in function space, right? Meaning like you vary over size such that your expectation values are high, or something like that.
Yeah, so the point of these paradoxes is that such a construction will not work.
Will not work.
Will not work. So the paradoxes tell you that nothing you can do will allow you to, you might have thought that maybe we'll do something clever to make something work globally, but the point is that the point of the construction is to tell you something like this will not work. The point of the paradoxes is to tell you something like this will not work. So these paradoxes for large black holes tell you this will not work.
Right. I was trying to see if there's some simple way to see. Well, I guess that is the simple way. Is what it's through the.
Let me just say a few things, and maybe we can discuss again.
Okay.
Great. Okay. So what do we do here, right? So we have this conclusion. We have these mirror operators that work in some states. We can't find something that works in all states. So we have a few things. We could say, well, okay, typical states are firewalls, or the boundary doesn't describe the interior of typical states. But then, as we discussed, we would also run into trouble with the eternal black hole. And so there is another option, which is called state dependence. And in state dependence, we abandon the idea of trying to find a single operator that works in all states, but rather we declare that the infalling observer in the state psi automatically uses the mirror operators from H psi, or from the little Hilbert space constructed about psi. So why? Said another way, there are no global operators, but the operators used depend on the state. So let me first point out, why is this unusual? So why is this unusual? So why unusual? So this is unusual, first of all. It's unusual because this is not what we usually say about observables. When we open books on quantum mechanics, there's some postulate which tells us, here we have some set of Hermitian observables, and here there's a system, and there's some observables. There's an observer, and the observer can probe the system with different kinds of observables. And these observables are fixed once and for all. You can, of course, put the system in different states. But if you ask a physical question about the system, such as, let's say you ask a question like, what is the probability that the state has some feature? Okay. And the feature could be anything. State has some feature. For instance, the feature could be, what is the probability that it has a firewall? Say it has, what is the probability a state has some firewall? Or the feature could be something else. What is the probability the state has some big excitation of the black hole? Or what is the probability that the black hole has some mass or something else, right? So it could be any feature. So when you ask usually in quantum mechanics a question of this kind, what is the probability the simple harmonic oscillator is in some state or something like that? Usually this question is answered by taking the expectation value of a projector in the state. So this answers this question, where this projector projects onto states that have that feature. And if you project onto states that have that feature, then you see that the expectation value of this projector answers this question for you. And these are the questions we usually ask. So we are allowed to take all possible states of the system, but then to every feature or to every physical observation, we associate ahead of time some observable or some projector, and sometimes we might take a Hermitian observable, and then we ask about the expectation value of that projector in a state, and that answers for us a question of this kind. Okay, so here we see we are doing something different. We are saying there is no operator that will tell you what the correlator of the field inside and the outside is, but rather the operator that you have has to depend on the state, which is not what we do usually. So this is why it's unusual, but why is it conceivable? So why is it even conceivable? The reason it is conceivable is that the kind of question we are asking in black hole physics is a different kind of question from the kind of question we ask usually. If you look back at this picture, you will see that usually when we ask these questions and the way quantum mechanics is formulated, questions are asked by imagining that there's some system, and these fixed observables have to do with an external observer who interacts with this system. And that external observer has some fixed basis of observables or fixed basis of ways in which the observer can probe the system. And that is what leads to this fixed basis of observables. Okay? So the reason this is conceivable is because we are asking an unusual question here. And the unusual question we are asking is that the observer is part of the system. And because the observer is part of the system, we say that the observer uses the natural basis of observables available at the horizon. And this natural basis of observables may depend on the state. So that is the reason that something like this is conceivable. Of course, said another way, one would not have thought of some proposal of this kind. One would have resisted some proposal of this kind. But one is forced to this kind of a proposal by the paradoxes that one finds for large black holes and also for the eternal black hole. And so if you would like, or if you believe that the boundary theory or ADS-CFT does give you a description of the interior, then or the typical states don't have firewalls, then you're forced to this kind of state dependence feature. And the reason the state dependence is conceivable at all is because we are asking a different kind of question from the question we usually ask in quantum mechanics, where there is some fixed basis of observables that the observer external to the system has. And here we do not have such a fixed basis of observables because the observer is part of the system. Okay? Let me just say one thing. And the thing is that, the way we constructed the mirror operators, the state dependence is invisible to the infalling observer. And the reason it is invisible to the observer is because to the infaller is that we said that the infalling observer measures some correlators of this kind. Right? The infalling observer measures some correlators of this kind. But in such correlators, the fact that in such correlators, A omega tilde is fixed. In fact, we designed it to act linearly on the little Hilbert space. Right? It acts linearly on the little Hilbert space. And what is more, you can take products. So it behaves exactly like a usual operator. So if the infaller measures some correlators of this kind, the fact that this observable is not the same. So the fact that this operator is not the same in some other microstate is totally invisible. It's invisible by construction because to go from psi to psi prime, you need to go outside the little Hilbert space. And we have forced, we have by fiat declared that that is something that the infalling observer does not ask. That is something which is not well described within bulk effective field theory. And so for the kinds of questions that we have been discussing for the infalling observer, it is important that the state dependence is completely invisible. So it is not like we are saying that, look, we are just giving you some answer that we want for the infalling observer, but rather we have some operators that do work correctly, that behave perfectly like ordinary simple operators within the little Hilbert space. They act perfectly linearly. If you take this operator, you take AM psi and take like a different AM psi plus AN psi, this acts perfectly linearly. And so the infalling observer doesn't see the state dependence, right? So there's no state dependence here. So the state dependence is at some level of when you make a transition from one microstate to another microstate, which is in some sense very far away, in that it can't be reached by simple operators or by simple observers. And so the infalling observer just sees ordinary quantum mechanics. Okay? So the infaller just sees ordinary quantum mechanics. But nevertheless, in order for the infaller to see ordinary quantum mechanics, you need secretly that these operators that the infaller is measuring are state dependent, and they vary from microstate to microstate. So I did a little bit less than what I wanted to say. Let me just say one thing about, let me just make an advertisement for next week and we'll stop. Yes, sorry.
Can I ask you a question? So,
yeah, sorry, can I just say something before we, sorry,
okay,
can I
sure, go on.
So I just want to make before I conclude, since we are out of time, I just want to say one thing. So we will see in the beginning of the next lecture that this use of state dependent operators will resolve all these paradoxes. So it really will resolve all the paradoxes that we found for large black holes and also for the eternal black hole. Okay. So, and the reason is actually quite simple to understand. I won't do it in detail, but let me just say in words what the reason is. You see, let me remind you that all of these paradoxes that we constructed were never constructed by asking about some simple correlator or asking about some simple observable and saying, look, here's a paradox. They were always constructed by using a trace. They all involved a trace. Okay? And they all involved a trace. And when you do a trace, you necessarily sum over a basis of microstates, which are all very different and which are not related to each other by simple observables. And if you do not assume that the operator stays fixed as you perform this trace, so as you range over the entire Hilbert space, then these paradoxes do not apply, as we will see explicitly next time. But as should already be obvious from the fact that when we develop these paradoxes, we emphasize that each of them involved a trace. Okay, so let me actually just stop here with this interesting idea. I think this issue of state dependence is an extremely interesting idea. In the next week, we will also discuss how state dependence itself might give rise to puzzles. Even though it resolves all these paradoxes, it might itself give rise to additional puzzles, and we will discuss the extent to which those puzzles can be resolved. But since we're out of time, let me stop here and postpone this discussion to next week, and also take any more questions that are there.
Yeah, can I ask? So like I understand, like we landed on a state-dependent construction of interior observers and so on, observables and so on, and the infalling observer can't really see the state dependence. But
right.
What is an experimentally possible way to really say that A tilde, the interior modes constructed in different states, are different? Like
yeah,
we are saying it's different for different states of the black hole, but how do you even experimentally make that statement?
So so experimentally within bulk effective field theory, it's not a statement that can be made. To be able to make the statement, you would need some observer who can compare like the state psi1 with some totally other different microstate, and then start asking questions of this kind. So
like
you'd need
even if you say black hole is some tabletop condensed matter system, like is there a way you can make this comparison? I don't understand.
If you had a tabletop condensed matter system and there was a way of comparing the if there was a way of comparing the experience of infalling observers in different microstates. So you have an infalling observer, the infalling observer falls into one microstate, and you have a way of comparing the experience with the infaller in a different microstate, then you would be able to see the fact that you had this state dependence. But you would have to,
naively speaking, like the outside modes are same for any state, right? Anything else, and so I'm trying to understand this statement as something like this. say the black hole was some condensed matter system like a metal or something, and you send in an infalling observer like a electron or something which you inject into the metal, and it seems that the metal, the quasi-electron which appears, which propagates inside the metal, depends on the state of the metal rather than. Right? Is that the correct
that's
statement?
clearly not the case. So anything you do from outside is not the case. So you see, that's why I said we're asking an unusual kind of question. You're trying to ask, you created an infalling observer, and what is the experience of the infalling observer? So of course, if you're just an observer who just observes something on the boundary, then there is no that you don't need the state dependence and you don't need these operators. But here you're trying to ask a different question, which is you have an observer who falls through this big black hole, and what did the observer see? Did the observer see a firewall, or did the observer see something else? Which is not naturally defined as some question on the boundary. So we are trying to find some effective field theory way of describing the experience of this infalling observer. And if you had some way to fish this observer out of the black hole at a later time, then you could try and query this observer and ask, is there a
which
sense?
is not possible, right? So I don't see any way you can really.
Well, it's not impossible if you have arbitrary, if you have arbitrary paths. So for instance, you could at a later time you could turn on some coupling or something else which would make the black hole vanish, and then you could try and phrase this question maybe purely on the boundary. So you're right that it's a difficult question to ask just on the boundary, and the question we're asking is more naturally defined in the bulk and not in the boundary. So you're right that there's you're right that it's not a natural boundary question, but it is a natural bulk question. It is a natural question in the bulk. And it's of course true that if you just ask questions about boundary observables, then you won't see any state dependence in any natural way. But if you had a way where bulk observers could compare the experience in psi 1 and psi 2, and they were arbitrarily powerful and they were super observers, then they might see. Then there would be some sense in which they would be able to see the state dependence. And I should say that just let me say one more thing. Sorry, there are some other features of the state dependence. So when we discuss the consistency of these state dependent maps, I'll describe some other statistical mechanics inequalities that these state dependent observers might violate within simple correlators, or that is also difficult to observe. But at least within correlators, you can frame an effective field theory. And if a bulk observer could do that, that would give indirect evidence of the fact that you were seeing state dependence, although not direct evidence. But I'll describe that in more detail next time. But go on.
I'm slightly also confused. Like, why can't I completely rephrase the description of interior observables as state dependent to the state in the interior as state dependent?
Sorry, I did not understand that. Can you
as
say
in any state dependent, like whatever we are calling state dependent, has to be can be observed only if you go into the horizon, right?
Correct.
So why is it? I'm confused why it can't be rephrased as how the A tilde modes are populated are to be are in some sense state dependent.
What do you mean how they are populated? These A tilde omega operators in the boundary Hilbert space are in some, like different operators in different microstates. And you're right that
but you have to really go into the black hole to, even for a bulk effective theory observer, you have to really go into the horizon to observe that.
You have to go into the horizon to detect the A tildes, and within simple experiments that you do, like within infalling observer, like does simple experiments, you don't see the state dependence. So it just looks like ordinary bulk effective field theory. And that's why, these things are designed so that it just looks like ordinary bulk effective field theory. But it's true that, in some deep sense, like, if the infalling observer had fallen into a different microstate, then the operators the infalling observer would have interacted with would be different operators in the different microstate. And you're right that, within effective field theory, there's no way really to compare one observer in one microstate with the other observer in the other microstate. So it's like a cosmological question. One observer is in one universe, the other observer is in a different universe, and then they can do some effective field theory experiments in each of these universes, but they can't really compare what each of them saw. And so you're right that to that extent there isn't a contradiction, but it is true that from the boundary point of view, the observers we're using to describe the experience of the observers is the operators are distinct operators in distinct microstates.
Right.
And you also
And-
yeah.
Right, thanks. And also, like, if you really have a CFT description, there should be a purely condensed matter question we should be able to phrase, right, which sees a state dependent answer.
I'm not sure that there should be some, there is no, you see, if you ask about the boundary, then all of these issues don't really arise, right? If you just ask questions about boundary observables, then, you just ask questions about boundary observables. And some of these questions are, are natural bulk questions. And we are trying to map them to boundary questions. So if you like, this map, kind of tells you what you should measure to see what the interior operator sees. But it's not a, this A omega tilde, we wrote down some construction, right? So in principle, this correlator we have now translated to some boundary correlator. So the statement would be, you measure this correlator and this tells you what the experience of the infalling observer is. But from the boundary, you could say, why do you measure this correlator? What's special about, this combination? And there's nothing, there's no natural, this is not a natural thing to measure from the boundary. It is something you can measure on the boundary.
Can I ask a question of interpretation? Right. Oh, sorry.
Sorry, I just had a follow-up to the earlier question, if you don't mind.
Sure, yeah.
Yeah, so I was just a little confused by the statement that you can't see state dependence from the boundary. I thought, you can't, it might not be natural from the boundary, but you can still see it in some sense, right? In the sense that you could compare what would be the experience of two infalling observers, but you could be on the boundary and just do a computation that would tell you that.
Right. Yeah, that could tell you that. I thought the question was, from the point of view of the infalling observer, how does the infalling observer see state dependence? Because on this slide, what I was pointing out was that the infaller just measures some simple correlators and doesn't see the fact that a different infaller in a different universe, in a different state, would be using different operators from some fixed basis on the boundary. So I thought the question was, how would you make it visible to the infalling observer? And you would need some way to, you'd need some way for observers, for these infalling observers in these different universes to be able to communicate with each other. So you'd need, you'd need to break these limits we have put on what the infalling observer can measure. These limits about the observer only being able to measure effective field theory questions.
Right. But as far as like experimental tests go or something, you could in principle do an experiment on the boundary, which would kind of tell you.
But the experiment on the boundary,
it's not sort of natural from the point of view of the boundary, but it's still something that verifies state dependence in the bulk for bulk observer.
It's not something that you see. The point is that so here is what the infalling observer measures. Now you have to tell me what is A omega tilde. So if you use the state dependent prescription, then by construction, you're measuring a state dependent operator on the boundary, which you could do. You could say, in one state psi, I'll measure one operator, and the other state will measure another operator. But if you ask a question of, why does the infalling observer, how do you know that the infalling observer measures this A omega tilde and not some other operator? That's not something that we have a very good answer to. So these operators are constructed so that the infalling observer sees effective field theory. But from the, if somebody said, let me put it this way. Let's say somebody said, I don't think there's any state dependence. I think that the observer always uses like the same operators, and the observer always encounters a firewall. Then it would be there's no very good answer to that question, or at least we don't know what the right way to answer that question is. What we can answer is a question of, if you use state dependence, there's nothing that, you can describe the interior in some way. But the question of why it is that these operators describe the interior is not a question that we have a good answer to. So let me say that more clearly. You see, if I just, your original question was, can you verify state dependence in the boundary? And of course, you could measure these correlators. And then you would have to tell me what A omega tilde is. If you chose A omega tilde to be the construction I just described, then of course you would verify state dependence. But that would be by construction. If you chose A omega tilde to be like something fixed, then you would, not verify state dependence. So, from the boundary, you have to tell me the question of what the infalling observer sees is not a natural question immediately on the boundary. And so I don't know of any way in which you could verify by making some complicated enough measurement state dependence or the lack thereof on the boundary. I don't know if I answered the question clearly.
Right. No, I guess I get it. I mean, there are I mean, you can think of each of these A tilde omega operators as defining some set of calculations on the boundary, but assigning which observer sees what is something that you can't do from the boundary.
Exactly.
You would have to actually go into the product to make that assignment.
Exactly.
Right. Okay. Thanks.
Yeah.
So if I can ask an interpretation question.
Yeah.
So
Yeah.
It seems to me that from the boundary point of view, you have full control over the theory, so you can change the state and so on. While this construction we have in the bulk, you have an observer that moves in a semi-classical, let's say, space-time and can only act within effective field theory. So do you think it's a viable interpretation of this result where an observer in the boundary in the bulk must measures naturally operators that are dependent on the state, while on the boundary it seems like you have full control of the theory? Do you think the reason is that the boundary, you can say that the boundary theory is in some sense the fundamental theory, and then you can see each of these space-times with their specific operators that are dependent on the state of the whole space-time and so on the state of the boundary as an emergent feature, and so an effective description of the low energy theory of the state in the boundary specifically, and that's why you cannot define a global bulk operator?
Yeah, that's right. So that's one reason that that indeed you're right. That one way to say this would be, that there's an effective emergent bulk description, and the effective emergent bulk description is emerges about a given state, and therefore you have to decide what that effective emergent bulk description is depends on which state you have. Yeah, you're right. That's certainly something you could say. I still want to emphasize that this is still something that's unusual, because this effective emergent bulk description, for instance, you could say also emerges, in empty ADS. And in empty ADS, you don't need to use this notion of state-dependent operators. So there is something that's unusual that's happening, and it's yeah. So you're right. That it is an effective emergent bulk description, and we are saying you need to use these state-dependent operators. And there's some fundamental description on the boundary where, of course, you don't have any state dependence. You have some set of observables you can ask, and if you try and translate it to some bulk description, then you need to translate it in the state-dependent way. But I think there's still something here which one shouldn't kind of push under the rug, which is the fact that there is something, there is some interesting phenomena that one sees here, and it may be related to the fact that one is asking in the bulk context a rather unusual kind of question. In a sense, this is the question we're asking for the infalling observer, but this is the question we could also ask in cosmology. We are observers in a universe, and why do we measure like some modes of the field versus some other modes? Or is the basis of observables that we select, is it somehow determined by the microstate of the universe? So I think it's also a more general interesting question one can ask when one asks about quantum mechanics in cosmological settings. I don't know if that answered the question. I said something,
Yeah, it does. Thank you. But just a follow up. But is it even reasonable to try and talk about because if you are actually an infalling observer, then you will just see naturally that basis of states, right? So the all this problem of state dependence, basis of observables operator.
Right.
But if you so when you actually see state dependence is when you try to consider different states. There are like radically different states in the Hilbert space. You consider operators in those different states. Right. But so from, let's say, semi-classical gravity point of view, that's not a question that really makes sense, because you're just an infalling observer that has a space-time, a continuum space-time, and so on. And so that's fine. And if you try to consider like a fundamental quantum theory where you have huge fluctuations, at that point, I don't think it's that obvious that you would have a description which is given by a continuum space-time geometry, right? So at that point, is it?
Yeah, I agree with that. Yeah.
No, I'm just asking, is it even like a problem that you see this? Do you actually see this state dependence?
Yeah, no, so I agree with you. I should say one thing though. which we'll discuss a little bit, I mean, maybe in next week, is that you're right that you don't directly see state dependence, but the fact that you use these state dependent operators does give rise to some slightly unusual features of the bulk theory, which is that, it, for instance, leads to the fact that these black holes are unusually sensitive to low energy excitations. So I'll have to try and explain that in a little bit more detail. But there's some statistical constraints you can derive on state independent operators that tell you that if you make a low energy excitation, the expectation value of the operator shouldn't change much. But for these black holes, if you use these state dependent operators, a bulk observer would observe that you could make some low energy excitations that could change the structure of the horizon. And so there would be some indirect signals you would get of this state dependence. So that, as I said, I'll try and describe that in some more detail. But once again, even there, you don't see any direct signals of the state dependence. And so that is certainly a position you could take. You could say that, the bulk theory is just not like fundamental. It's only the boundary theory which is fundamental. And if, this is just, it just so happens that if I'm given a state of the boundary theory, I want to interpret it in some bulk way and in some approximate semi-classical bulk way. And then I use these observables and I see I get an approximate semi-classical description. And, so what if I have to use different observables in different states? In fact, one thing that we discussed previously and we'll discuss again next week is that, even the entanglement entropy has this property. That it's a state dependent observable. So the entanglement entropy is not given by the expectation value of any fixed observable. And so to the extent that the bulk spacetime has to do with entanglement, or that's believed, it's another example of where you use some state dependent reconstruction of the bulk spacetime. So that's certainly one attitude which one could take. And I think it's a consistent attitude, barring some of these issues about these statistical mechanics inequalities that would give you indirect hints of this state dependence, which we'll describe in more detail next time.
Thank you very much.
In the discussion of near equilibrium states, we excited with operators in the exterior, unitary operators in the exterior, but we could have excited with operators in the interior as well, right?
Mm-hmm. Yes, we could have. Yes. So yeah, we could have, and it would. But those excitations can also be detected if you measure correlators of the Hamiltonian
yeah.
and other things. So because the interior operators don't don't commute with the Hamiltonian, you would also be able to determine like those excitations if you also measure correlators of the Hamiltonian, and so you would be able to define mirror operators for those as well.
Thanks.
Yeah. Any other questions? Okay, so then we'll resume our discussions next week. Yeah, we've kind of ended at an interesting point, and so next week we'll continue these discussions then.